Hey, welcome back everybody. Alright, we're moving on to section 4.7, and we're no longer going to be focusing on just proving that triangles are congruent. Now we're going to be looking at using isosceles and equilateral triangles, and essentially all that I'm expecting you to be able to do is to use properties of isosceles and equilateral triangles. Real simple properties for you to learn here, real simple properties to apply. Alright, let's try it out. First, I need to teach you some terminology. I've got a couple of isosceles triangles drawn, and what I'd like to teach you about is what are called the base angles of an isosceles triangle. Okay, now, in order for me to do that, I kind of need to share with you what's called the base angles theorem. So let me do so. Anytime you have a triangle where there are two sides that are congruent to one another, it turns out that always the angles that are opposite those sides are also congruent to one another as well. So, if segment AB is congruent to segment BC, then the angles opposite those sides, which the angle opposite from side AB is angle C, right here, and the angle across from segment BC is angle A right there, then those angles opposite those congruent sides are congruent. Angle A is congruent to angle C. It's always going to be true that a triangle has just as many, if you're talking about a single triangle, it will have just as many congruent angles as it has sides. So if it's a scalene triangle, it won't have any congruent sides or any congruent angles. If it's isosceles with two sides congruent, it's going to have two angles congruent. And equilateral triangles will have three congruent angles. Okay, now, I said I was going to teach you some terminology here. Those congruent angles of an isosceles triangle are called the base angles. By the way, a lot of people hear the word base and think it's got to be the bottom of the figure. It doesn't. The base angles of an isosceles triangle are simply the congruent angles of that triangle. And then the other angle has a name as well. It's called the vertex angle. But to summarize, the base angles theorem is that, simply in my own words, if a triangle is isosceles, then its base angles are congruent. Now, I drew two triangles here because it turns out the converse of that is true as well. If I flip that statement around and I tell you that I've got two angles in a triangle that are congruent, such as angles D and F, any triangle with two congruent angles is automatically going to have two congruent sides as well, the sides opposite those angles, which would be segment DE opposite angle F, and then segment FE opposite angle D. Those would have to be congruent. Okay, that's the converse of the base angles theorem. All right, again, if a triangle has two congruent angles, in this case, if angle D is congruent to angle F, then it's going to have two congruent sides, the sides across from those angles. In this case, segment DE is congruent to segment FE. All right, now I said we're kind of moving past the part where we're proving that triangles are congruent, but I want to show you why we cared about learning the triangles, how to prove that triangles are congruent. It helps us prove little facts like the one that I just showed you in the base angles theorem. And because of that, I want to show you the proof that the base angles theorem works. And so I'm trying to show you that if a triangle has two congruent sides, it's also going to have two congruent angles. Now, we're going to do some stuff that you're used to doing with proofs, and then we're going to do something that you're not used to doing, and it's done in special cases for a theorem like this. We know that those two segments are congruent. Now, if that's all we knew based on the definition of isosceles triangle, it wouldn't have to mean that angles Z and Y are congruent. But we can prove that they have to be if we can make this triangle into two triangles, and we're going to do that by drawing the altitude from the vertex angle to the bottom of that isosceles triangle. Now, when I say we're drawing an altitude, it's automatic that an altitude is going to be perpendicular to whatever side of the triangle you draw it to. So that's going to make these right triangles. And can you see how whenever I draw that altitude, it creates two triangles that are congruent by HL, because you got the side they share, you got the hypotenuses that are congruent, and they're right triangles? Okay, that's going to be involved with our proof here. So let's state segment XZ is congruent to segment XY. All right, and this next part you're not familiar with, but that's fine. I'm just using something that I kind of know ahead of time for you. I'm going to say that segment X, M, I named this little point M right there, is an altitude. And because it's an altitude, that means it's going to be perpendicular to segment ZY. That's based on the definition of altitude, which means that angle XMZ and XMY are right angles because of the definition of perpendicular lines. And remember, I'm going with this right angles thing because to use HL, you got to prove that two triangles are right triangles, and that's what I'm going to say right now, is that triangle XMZ and triangle XMY are right triangles. Based on the definition of right triangles. Now, I've proven that the hypotenuses are congruent in this statement. I've proven that the triangles are right triangles. I still got to prove that they have a pair of congruent legs. So we're going to now say that segment XM is congruent to segment XM. The reflexive property, of course. And then two more things here we'll try to squeeze in. We've now given enough information to prove that triangle XMZ is congruent to triangle XMY based on HL. And what was the whole point of that? Remember, I was trying to show you that if a single triangle XYZ has two congruent sides, that it also has two congruent angles. Well, angle Z and angle Y are corresponding angles for these two right triangles right here. And since those two right triangles are congruent, now we can have proven that angle Z and angle Y have to be congruent using CP/CTC. Now the takeaway from that isn't that I need you to be able to prove the base angles theorem. You can just use the base angles theorem. But I wanted to explain to you that the reason that we're learning how to prove that triangles are congruent is because it helps us prove properties, useful properties, for all types of figures, not just for isosceles triangles, but for quadrilaterals, pentagons, all those different things. All right, now on to the isosceles triangles and the equilateral triangles. And this part, pretty easy. One little thing I wanted to write about equilateral triangles here is that the base angles theorem applies to them as well. Now, since segment AB is congruent to segment B in this picture, that means that angle A would have to be congruent to angle C. But if you keep looking around, since segment AB is congruent to segment AC, that means that angle C has to be congruent to angle B. And can you see how by the transitive property then, all of the angles of an equilateral triangle have to be congruent to one another? All right, so equilateral triangles are always isosceles, and vice versa. All right, and that fact and its converse are both correlators to the base angles theorem and its converse. You can check that out in your textbook, though. Let's get on to using this information. All I'm asking you to do in these next several examples is to find the values of the variables and using what you know about isosceles triangles. Which sides are congruent, which angles are congruent, and how can you use that to your advantage? Well, let's look at this triangle in part A. You see that two sides are congruent to one another, and so automatically you ought to say, well, I know then that the base angles of that triangle are going to be congruent to one another as well. So, whenever I'm trying to find x, the vertex angle here, I know what the other two angles are because they're both congruent to one another, right? If that other one's 70 degrees, this one has to be 70 degrees. And then I can just simply say that x plus 140 is equal to 180 because that's how many degrees are in a triangle, right? And so I can figure out that x equals 40. And then how about the value of y? One of the things that you need to do is realize whether a variable represents a side length or an angle measure. X represented an angle measure, correct? So it made sense to add up these angles to 180. Y is part of a side measure. All right, the side measures don't have to add up to anything in particular, but these two segments are congruent to one another, right? So you can say y minus 7 equals 18, and y equals 25. All right, really I would like throughout these next several examples, if you would just, when you see the picture, try it on your own, and then just check back with me for an explanation to see if you got it right. All right, so I would recommend doing that with part B right now. All right, now you can see from the markings in the diagram that this triangle is equiangular. So each one of these angles we could say then is x degrees. And that would tell us then that 3x equals 180. And x equals 60. I think you probably already knew that an equiangular triangle has 60-degree angles. And then because the triangle is equiangular, we have said that already. That means that the triangle has to be equilateral as well. And so this side right there that's 21 units long and this side that's y units long have to be equal to one another. There's our value of y. Easy stuff, right? Let's keep going. Now they're going to start getting more difficult at the bottom here. See how you do with this one, obviously, part C, before you do part D, though. Now for my explanation here, I'm going to copy this triangle over. And then I'm going to erase that 3x and the 5y because I want to prove a point to show you how to make this simple. You see that this is an isosceles triangle, and the fact that it's a right triangle is important as well. Since it's an isosceles triangle, two sides are congruent. That means these angles would be the base angles, and they'd be congruent to one another. And also remember the corollary to the triangle sum theorem says that the two acute angles of a right triangle are always complementary. So each of these angles is going to have to be 45 degrees if they're going to add up to 90 and be equal to one another, right? And if you were able to figure out that those two angles had to be 45, then you were able to work and solve for x and y. Because it didn't do you much good to say that 3x equals 5y, even though it is true that this angle equals this angle. What does do you a lot of good is to set 3x equal to 45, because that'll give you x equals 15, and set 5y equal to 45. That will get you y is equal to 9. Alright, now the pictures get a little bit more complicated. We've got triangles within triangles. There's 3 triangles in this picture, but it's the isosceles ones that I care about here. Okay, now I'm just going to start with this explanation. If you haven't already paused to try this on your own, you probably need some help with this, I'm thinking. You see here that this triangle is isosceles, right? Because it's got 2 congruent sides. That would indicate that this angle and this angle are congruent. However, that alone is not enough to find out what y is, because it's not an equilateral triangle, is it? Not that we are aware of anyway. And so we can't say they're all 60 degrees. And if you don't know any of the angle measures in a triangle and it's not equilateral, you need some help. Well, the help is going to come from this other isosceles triangle. You can see that this second triangle also has 2 sides that are congruent to one another, which means that it's going to have its base angles here and here congruent to one another. Now, this is where our help is going to come from in terms of finding out the value of y. If this angle is 25 degrees, then this angle would have to be 25 degrees. And then if you add up 25 and 25 and subtract from 180, you're going to get 130 degrees right there. Which then, if we use the linear pair postulate, helps us conclude that this is a 50-degree angle. So there's another 50-degree angle. And then add 50 and 50 and subtract from 180. And you're going to have y is equal to 80. So that takes care of what the value of y is. We still have to work with x. Well, we're going to use a little transitive property here to figure out what x is. There are 2 segments that we know the length of. You can tell that this one's 20 units long, this one's 23 units long. But we need to be able to find which one relates to this x minus 11 unit long side. Now, x minus 11, you would agree these 2 segments are congruent because they're marked as congruent, correct? And then this segment is congruent to this segment, isn't it? Because those are also marked as congruent. So by transitive property, we can say that this is 20, which means that x minus 11 is also equal to 20. And so there you get x is equal to 31. All right, one more example to try. Now, I didn't give you any numbers inside of as far as the angle measures go for this triangle, but I've given you quite enough information to find the value of x, and I've given you enough information to find the value of y as well, even though I haven't told you that any sides specifically are congruent. See what you can do on your own, and then come right back and listen. Let's start with the angle measures here. You notice that there was a triangle here that has all three angles congruent to one another, and another triangle that has two congruent angles. Well, let's start with that equiangular triangle. We know that all the angles in an equiangular triangle are going to be 60 degrees. Okay? And then we can either use the linear pair postulate or the exterior angles theorem to find this angle measure right there, and that it's 120 degrees. And so now we're able to say that x plus, well, that's x, and this is going to be x as well. X plus x, or 2x, equals 60. All right, that's what 120 subtracted from 180 is, and that means x is going to be equal to 30. All right, now, as far as the side length goes, finding that 2y minus 1. That bottom left triangle that's equiangular, we know has to be equilateral as well. And then we know that the other triangle, that obtuse triangle right there, it has two angles that are congruent. So according to the converse of the base angles theorem, it's going to have two sides that are congruent. So all four of those segments, these three and this one, have to be equal in length, which means that we can ultimately say, if you follow this path right here, that 2y minus 1 is equal to that, which is equal to 7. So y is going to end up being equal to 4. All right, so isosceles triangles not only have two congruent sides, they have two congruent angles. That's one of their properties. Equilateral triangles have three congruent angles. If you understand that, then you've got the main point for section 4.7. Just a matter of working out some problems. Thanks for watching, guys. See ya.